Okay, good morning, everyone. Let's get started. So does the screen look okay? Yeah. Okay. Looks like there are fewer students joining maybe because of the weather. It's getting colder, right? Oh, nice. Yeah, we have more students coming in. Yeah. Okay. So I just want to emphasize that homework 3 has already been released, and compared to the workload of homework 2, the homework 3 is really lighter. I mean, the workload, but don't rush at the last minute. I mean, in the homework 2, our experience is that okay, too many students are, running into the office hours in the last like 2 or 3 days. So I heard complaints about the congestion. You're always in the queue, you cannot get enough help. Well, we are trying our best. We provide office hours every weekday. But most of the time, 99% of time is empty. So of course, if everyone run to the office hours in the last 2 or 3 days, of course, we're not able to like completely cover everyone's need. But if you could start early, seek for help early, that would be much more convenient. Most of the time, honestly, our TA are just sitting there and doing their own stuffs, right? No one stops by, and so do I. So yeah, again, like if you need some help, and if you want some help, just stop by the office hour early, and especially for the homework 3, right? So the homework 3 is all about, I mean, the programming section is all about the perceptron. I believe it is relatively much easier, but you still need some time to debug. Right? You still need some time to get reasonable results. Right? So again, don't wait until the last minute. Okay, and a second thing is about how do we carry out the final exam. I've heard some request for like having this exam online. We did this, I think, in the past 2 years because of the COVID. I mean, in this semester, theoretically speaking, we can do in-person final exam. But of course, if you want to do the online, it's still feasible. I will make a vote on the Canvas. So feel free to vote, and we can decide in whichever way you want to take the final exam. Okay. Okay. So far, any question regarding the homework settings, then project reports, or all kinds of other stuffs? Okay, great. So let us continue with this dimension, right? So we first do a quick review of what we discussed last Thursday. So in the last lecture, we talked about another learning settings called agnostic learning, right? So in contrast to the consistent learning, agnostic learning makes a much more realistic assumption that your target function is not necessarily inside the hypothesis space of your learning algorithm, right? So it is possible that, let me suppose this is your hypothesis space, right? Your learning algorithm is gonna search some hypothesis inside this space. Like for the consistent learning, which assumes that you always get zero training error, the implication is that, okay, your target function is always inside the hypothesis space, right? But it's too strong. That's too strong assumption, right? More realistic assumption will be that, okay, your target or your concept function is here, right? It's not necessarily inside the hypothesis space. That means you're not guaranteed to have zero training error all the time. Right? It is possible that you have some data set, you try your best to find a hypothesis which is close to the target function, but you still cannot match the labels provided by the target function. Right? That means you might have like non-zero training error. Right? So we discussed in such a case, how do we still estimate the generalization error, right, based upon the training error? Right? Remember, in the agnostic learning, your training error is not always zero. Right? So here's our results. We used half-density inequality, one-sided half-density inequality to derive an elegant solution, namely the sample complexity bound, right? So the claim is that, okay, given epsilon, which is the relative difference between the training error and the generalization error, right? And also delta, which is kind of like probability level or confidence level, right? If your number of training examples is at least this, right? Then with high probability, meaning that with probability at least 1 minus delta, your true error will be in epsilon away from the training error, right? So here, just to be careful, when we talk about conclusion about agnostic learning, we're never saying, okay, what is the absolute level of the true error or the generalization error? Because we don't have zero training error, right? So we're talking about the relative difference between your generalization error and your training error. Right? We can claim that, okay, if you have enough number of examples, like at least no less than this lower bound, then your true error will have a large chance to be just in epsilon away from the training error. Okay. So from this bound, we can also derive a generalization error bound, right? Which is simply switch m and epsilon in the equation. Epsilon is, remember, it's difference between the generalization error and true error. That gives us a conclusion that, okay, for any number of training examples, for any confidence level, right, we can claim that with high probability, with probability at least 1 minus delta, the generalization error, the difference between the generalization error and the training error is upper bounded by this guy. Right? And this guy is determined by the size of training data, the confidence level or probability level, and also the log size of the hypothesis space. Right? So talk about the meaning of this term. Right? This actually reflects the complexity of your model. Right? Your hypothesis space. We can imagine that the larger the hypothesis space, then the larger this upper bound. Right? That means the larger the estimate of your generalization error. This gives us another justification of the Occam's razor's principle. Right? So given the same training error, right, the smaller your hypothesis space, meaning the simpler your machine learning model, then the smaller the bound. That means the smaller the estimate of your generalization error. Right? That's why we prefer simpler hypothesis space, simpler machine learning models. Right? However, these are not enough because so far in consistent learning and agnostic learning, we in this analysis we always assume, okay, your hypothesis space is finite, which is unrealistic as well. Like even for linear classifiers, we know that the parameters W and B are continuous. That means your hypothesis is infinite. Right? For infinite hypothesis, all those results are not meaningful because you're going to get a lower bound, which is infinity, right? Which is not meaningful at all. So then it motivates us to develop a measurement of the expressivity or complexity of the hypothesis space. Even if hypothesis space is infinite, can we work out a measurement or finite measurement, right, which can indicate its expressivity so that we can compare different infinite hypothesis spaces. Even they're infinite, their expressivity can be different. Right? We gave some kind of examples in the last lecture, like rectangles versus general convex polygons. Of course, the latter is more expressive. Right? So right now we can view like VC dimension for a hypothesis space is kind of counterpart to the size of hypothesis space. Right? But it is more useful in that when the size hypothesis space is infinite, the VC dimension in most cases are still finite. So we can use that to compare, measure the expressivity for a larger or broader set of hypothesis spaces. So I'm gonna skip this motivating example, right? So VC dimension is defined on an important concept called shattering. Right? So what does shattering mean? So basically, you can view like H is a set of candidate functions, right? A hypothesis space. We see, for example, we use lines as our hypothesis space, meaning our hypothesis space includes all kinds of lines, right? So if we want to look at 2 points, right, we'll see that these 2 points, this particular 2 points, can be shattered by our lines when for any labeling over these 2 points, we can always find a line in our hypothesis space which gives a 100% accurate prediction. Right? So for two points, we got 4 possible labelings. Right? Here, I emphasize that we still restrict our discussion about the binary labeling. Right? So we got 4 possible labels. So you can see that for all 4 possible labels, we can always find the corresponding line which correctly separate out positive and negative examples. So then we claim that our hypothesis space, namely linear functions, are expressive enough to shatter 2 points. Right? Then we discuss about 14 points. And unfortunately, our lines, right, our line hypothesis space cannot shatter 14 points. Right? Why? Because we require that for every possible labeling over these 14 points, if you can still find a corresponding line which can correctly separate out all the positive from negative examples, well, you can say, okay, our line hypothesis space can shatter its 14 points. Unfortunately, this is infeasible, right? For one case, like, okay, for this simple labeling, well, we can find a line to separate out positive and negative examples, right? But if you do a much more mixed labeling, right, there will never be a way to find a line which can, separate positive and negative examples correctly, right? So you can try this many times. That won't be possible, right? If you really want to separate all the positive and negative examples, you have to use some curve. Then the conclusion is that for this particular set of 14 points, they cannot be shattered by our line hypothesis space. So I hope this these 2 examples can give us a kind of intuition about definition of shattering, right? So now we look at the formal definition of shattering. So what is shattering, right? We say that a set S of examples is shattered by a set of functions H. Well, we can view H is a hypothesis space, right? If for every partition of the examples in S into positive and negative examples, there is a function in H that gives exactly these labels to the examples. So basically, you can consider like arbitrary set of examples, right? For any particular set of examples S, we claim that S is shattered by H if every possible labeling over the examples in S, you can find an instance in H that can predict the labels. Then we call S can be shattered by H. Does it make sense? Okay. So obviously, I mean, the first intuition will be, okay, the richer the set of H, the more likely they can shatter a larger set of points, right? Because you have more candidates, right? So now we want to do several concrete examples to reinforce our understanding of shattering, right? So let us consider a very simple yet infinite hypothesis space, right? So each instance in this hypothesis space is a left bounded interval. So basically, this interval where the left bound is simply 0 and the right bound is A. A is kind of positive value, right? Because A is continuous, so you have infinite number of choices. That means you have your hypothesis space is infinite. Right? So our classifier, left bounded interval classifier, is defined as follows, right? For any points inside this interval, we label it as positive, right? And outside this interval, label as negative, right? So, of course, our hypothesis space consists of all possible left bounded intervals, right? So now we want to analyze how many points can be shattered by our hypothesis space. Right? So first, can our left interval hypothesis space shatter one point? Yes. Yeah, I saw quite a few are nodding, right? So we can do some kind of analysis, right? For any positive example, right? Let me draw something here. Right? For any points here, right? If it is positive, right? If I want to correctly predict it, I can just pick up a suppose this is 0, right? I can just pick up A to be on the right of that point, right? So I can make a prediction, right? If this point we label it as negative, right? And then I can pick up the A value to be less than this point, right? So I can give a correct prediction. Remember, our classification rule is that, okay, if this point outside the interval, it will be classified as negative. Right? So now, let us increase the number of points to 2 points, right? For the 2 points, can we still shatter? Can our left bounded intervals still shatter 2 points? And not necessary, right? Like we need to follow the definition, right? Shattering means that, okay, you need to check every possible labeling on these 2 points, right? If for every possible labeling, you can find a left bounded interval, give a correct prediction, while we can claim, okay, the 2 points can be shattered, right? Otherwise, it cannot, right? So if this is where the 2 points stay, right? If the left point, we give a label as negative, and the right point give a label as positive, you'll find that we'll never be able to find a right A which correctly predict both examples, right? So you can put, like you can try to enumerate, right? If you put A here, right, all the 2 points will be predicted as positive, right? That's wrong, right? So if you put A here, right, to be less than the smaller point, right, all the points will be predicted as negative, right? You have some mistake, right? If you put it in the middle, right? If you put it in the middle, well, you make a wrong prediction for both points, right? You make the inside point as positive and predict the outside point as negative, right? It's totally wrong. So then our conclusion is that, okay, although this left boundary intervals form a infinite hypothesis space, it can only shatter 1 point. It's very, very restricted classifier, right? It's not expressive at all, right? Even they have the infinite possible classifiers or choices, your hypothesis space. Now let us try to increase the flexibility of this classifier. Like now, we consider an intuitively more expressive hypothesis space, where each instance is a free interval. Like we do not fix left bound to be 0, right? We assume like left bound, right bound are both right free real numbers, A and B, right? And we just require that B is bigger than A, right? It must form a valid interval, right? So our classification rule is still the same. Like for any points inside this interval, we predict it as positive, and outside points predicted as negative, right? So first of all, this intervals, right? Interval hypothesis space is infinite for sure, right? Because both A and B are continuous values. They have infinite number of choices. And secondly, they can definitely shatter 1 point, right? So we can take a look whether they can shatter 2 points. Remember, the left bounded interval cannot shatter 2 points, right? But for for the intervals, like for the free intervals, suppose I can just choose arbitrary 2 points, right? Let's see if they can shatter 2 points, right? If they are both positive, well, it is easy, right? I can put A here, put B here, right? If they are both negative, negative and negative, it's simple as well. Like I can put AB here or put AB here, right? So now let us look at, let me put here. If I put the label for the left point as positive and label for the right point as negative, can we find a interval to give a correct prediction? Yeah, this looks straightforward, right? We can just put A here and B here, right? And if we put a negative label on the left point and right and positive label on the right point, can we find a interval? The answer is yes as well, right? You can put A in here and B here. So you can see that now our free interval hypothesis space can shatter 2 points. Right? Now let us try to push this forward. Right? How about 3 points? Unfortunately, this free interval space cannot shatter 3 points. Right? Suppose these are the 3 points, right? Here and here and here. I put a negative label on the point in the middle and put positive label on the two on the left and right points. Right? You'll find that you will never be able to find an interval which can correctly predict all the 3 labels. Right? You can try that. If you put A and B all outside, they will give prediction on all the 3 points, right? You put A and B in here, right? You're gonna miss these positive examples. You put A and B here, you're gonna miss these positive examples. And if you put A and B in the middle, well, you give wrong prediction for all 3 points. Right? So you can do this. I'll leave this detailed analysis and enumeration for you. But you can see that if you increase the flexibility of this intervals, like we have like free intervals in our hypothesis space, you just be able to shatter 1 more points. Right? Now you can shatter 2 points. Right? So you can see that left bounded interval space and interval space, they are very, very restricted. So we can move to a third hypothesis space, which is called half spaces in plane. Well, we can simply view as linear classifiers. Right? This is just alternative term of saying like linear classifiers, because half spaces mean that you have a line or you have a plane, you have a hyperplane to separate to split the whole instance space into 2 half spaces, right? So if we look at the hypothesis of the linear classifiers, right, it is very easy to see that they can shatter 1 point, right? And from our previous example, we know that those lines or linear classifiers can shatter 2 points. Now we can see whether they can shatter 3 points. Remember, for our left bounded interval and intervals space, both spaces cannot shatter 3 points, right? And can line do this test? The answer is yes. Right? But to show that, you need to do a little bit more like tedious job. Right? Given this 3 points, right? You need to enumerate all possible labelings. Like there will be 8 possible labelings, right? For each labeling, you're trying to figure out a line in your hypothesis space, which can separate all the positive examples from negative examples. And for this particular 3 points, yes, the answer is yes. You can see that for every possible labeling, we can find out the perfect linear classifier. Right? So now we can claim that, okay, the half spaces or linear classifiers can shadow 3 points. Right? And the question is whether half spaces can shadow 4 points. Mm-hmm. No. Yeah. I know your point. We're talking about if there exist 3 points that can be shadowed by the half spaces. It's not talking about, okay, we must ensure like every possible 3 points, in the 3-dimensional space, whether they can be shadowed by the half spaces. Yeah, this is a very important point when we define the VC dimension. Right? So here we just give 3 points here, right? However, for some particular position of half spaces, like if you put it online, they won't be able to shatter by the half spaces. Right? You can check it out. But later we'll explain why we just emphasize on existence of a set of points that can be shadowed, right? Because that's the basis of the definition of this dimension. Right? I'll emphasize this point later. So the natural question, right, whether we can push further, right? So can half spaces shadow 4 points, meaning that if there are 4 points that can be shadowed by linear classifiers? Unfortunately, the answer is no. But I won't show why, right? This might happen, maybe might occur in your next homework. Okay, so basically, we can view shattering is kind of like adversary game, right? And you have an adversary, right? You want to claim that your hypothesis plus H can shatter this particular D points, right? And the adversary will propose, okay, that's what you think, right? I'm gonna propose a labeling that will defeat you. Right? And given this labeling, you say, okay, there is a function, your hypothesis space, that can correctly predict your evil labeling, right? And the adversary won't say, okay, won't claim that they lose, right? They'll say, okay, all right, your win is right, but I will be back. Right? So you can do this again and again until either you lose or the adversary lose, right? If you lose, you can now say, okay, your hypothesis space can shadow 4 points, can shadow D points. Some sets of functions can shadow infinite number of points, right? So that does not really say, okay, giving you an infinite number of points, you can shatter. It just says, okay, if arbitrary large finite subsets of the instance space X can be shattered by H, then we'll claim H can shatter infinite points. It's not like really you're giving an infinite number of points, right? So the intuition will be, or the takeaway is that, okay, the larger the subset of your instance space that can be shattered, the more expressive your hypothesis space is, right? So you can see the number of points that can be shattered can be some kind of measurement of the expressivity of your hypothesis space, right? Does it make sense? Right. So now we came to I will come to this VC dimension. Right? So this is definition of shattering, right? VC dimension is defined based on the shattering, right? So for any hypothesis space H, right? H can be finite, can be infinite. It doesn't matter, right? The VC dimension of this H over some instance space X is the size of the largest finite subset of X that can be shattered by H. So here's the subtle point. Might feel like a little bit not that intuitive. When do we say like your VC dimension is bigger than or no less than D? Right? That does not mean, okay, every possible D points must be shattered by H. Instead, as long as you can find out one set of D points that can be shattered by H, then we'll claim the VC dimension is no less than D. Does it make sense? Right. So this is a subtle point. Yeah. Like if you can find out, like going back to the 3 points case, right? If you want to look at the VC dimension of half spaces, right? If we can find out 3 points, as shown here, which can be shattered by the half spaces, then we'll claim that the VC dimension of the half spaces is at least 3. Yeah, it's not like, okay, you must have all possible 3 points that can be shattered. Right? As long as you can find one particular set of 3 points that can be shattered, then your VC dimension is like at least 3. Right? So this is a little bit conscious to our first intuition on that. Right? But this is our definition.
How will you be able to say with certainty that lines cannot shadow both lines? Because then you have to integrate everything possible.
Yes. That reaches to the second point of this VC dimension. Right. Let's go back to this. Yeah, that's a very good point, right? They're always ahead of what we want to say, right? Okay, the second point is that when do we say your VC dimension is less than D? It basically says if no subset of size D that can be shattered. So basically, if you want to say, okay, the VC dimension is less than 4, that means you need to show that every possible 4 points, they cannot be shattered by a hypothesis space. Okay. So just to keep in mind, this is I want to emphasize these subtle points in the definition of VC dimension, because in your homework, you'll be asked to show, like, for example, 4 points cannot like VC dimension of your like lines, like in the 2-dimensional plane won't be 4, and then you need to show that, okay, every possible 4 points cannot be shattered by your lines. Okay, so let me emphasize again, right? So VC dimension is the size of the largest possible finite subset that can be shattered by H, right? So as long as there exists any subset, as long as there exists one subset of size of D that can be shattered, then the VC dimension is at least D. Only when all subsets of size D cannot be shattered, then the VC dimension is less than D. Okay. Just keep in mind this definition. So here we give several like known results about the VC dimension for different classifiers. Like for half intervals, VC dimension is simply 1. Right? So that means for arbitrary 2 points, they cannot be shattered by half intervals. Right? For intervals, the VC dimension is 2. That means for arbitrary 3 points, they can be shattered. Right? For half spaces in a plane, that means lines, right? The VC dimension is always 3. That means for arbitrary 4 points, they cannot be shattered by the lines on the plane. And generally for linear classifiers, like linear threshold in D dimensions, the VC dimension is D plus 1. Okay. You're not required to prove that. I just keep it in mind. Right? D is the number of input features. And the visit dimension for neural networks is the number of the neural network parameters. So you can see why, like the deeper, the larger the neural network, the more expressive the neural network, right? Because it has a larger and larger visit dimension. Right? And interestingly, for a very simple classifiers called one nearest neighbors, the visit dimension is infinite. So basically, if you want to make a prediction, this one nearest neighbor classifier just to look at which training point is nearest to that test point and use that label as prediction. And this visit dimension is infinite. It's very, very expressive, right? Okay, so now we have a finished introduction of visit dimension, right? So we need to, we're only requested to know the definition of visit dimension and also the motivation of visit dimension.
If it's 1, 1, and we can always find this.
Yeah. If we see the visit dimension of the intervals is 2, that means at least you can find one set of 2 points, which can be shattered by intervals. Right? But the visit dimension is not 3. What does it mean? It means that okay, for any possible 3 points, they cannot be shattered by the intervals. That cannot be shattered by the space, by the half space. That's possible. Yeah, as long as there's something we just emphasized. As long as you can find out one particular set of points of size D, which can be shattered, then you can claim visit dimension is at this D. Right? It doesn't require that, okay, you must shatter all possible, all combination of the D points in your instance space. Any number of points. Yeah, I think you got confused about definition of shattering. Shattering means that you need to enumerate all possible labels, not restrict to one particular label. Like you can pick up any 16 points, right? But remember, you have a 2 to the power of 16 labelings. You need to ensure that you can find a line to separate out all possible labelings. Yeah, location is fixed, right? You can pick up any set of locations. You fix them, but you enumerate all possible labels on those locations. And for every possible labeling, you have to find a function in your hypothesis space, which gives a correct prediction. If you can do that, well, you can say, okay, I can shatter 16 points, but it's not, that's not easy. Yeah. So yeah, again, this is some kind of like starting point. When you do the homework, homework 3, no, homework 4, please do be careful about this definition. Okay, for the visit dimension, we request you to understand that the definition, right, as I've emphasized, right, and also why visit dimension, because we need some kind of expressivity measurement over infinite hypothesis spaces, right? You cannot directly use the size, because in that case, the size will be infinite, right? So for infinite hypothesis spaces, its visit dimension behaves like logarithm of size, right? So then someone asks, right, do we have some sample complexity bound, generalization error bound based upon visit dimension? Right? The answer is yes. Right? But here we will just give you the results. We won't look into how these are derived. Right? If you're interested, you can take a look at the Vapnik's classical book. It's called Statistical Learning Theory. Right? Those whole book is about like how do you apply all kinds of probability inequalities to derive those funds. You are not required to show those, right? So just need to understand those conclusions, right? So first, for the consistent learning case, right? Suppose you have a powerful powerful classifier, like you have a rich enough hypothesis space so that for every possible training data set, with some examples, you always find a hypothesis with 0 training error. Then we can claim that if M is bigger than this one, 1 over epsilon, 8 VC dimension times logarithm 13 over epsilon plus 4 logarithm 2 over delta, right? It's kind of like weird numbers. Then with high probability, the generalization error of your learned hypothesis will be less than epsilon. So this is kind of like similar structure as the sample complexity bound we derived before, right? But here the bound is up to the VC dimension, right? Rather than the log size of the hypothesis space. Right? And for infinite hypothesis space, right? For the agnostic learning case, sorry, it's not infinite. So for this agnostic learning case, we also have a version of the generalization error bound, which is up to the dependent on the VC dimension. Right? So we can show that with probability at least 1 minus delta. Right? That means with high probability, the true error, the difference between the true error and the training error, oh no, let's say in this way, right? The true error of the learned hypothesis with training error is bounded by this guy. Right? So you can see that bounded term is determined by the number of training examples, the VC dimension, and the confidence level delta. Okay? So you can see that the larger the training examples you have, right, the smaller this bound. Mean that the closer your true error to the training error, right? And the larger the VC dimension, actually the larger the bound, right? If you look at this VC dimension times logarithm 1 over VC dimension, it actually is monotonically increasing, right? So basically says, okay, the larger the VC dimension you have, then the more likely that your true error is far away from the training. In other words, like we still prefer smaller hypothesis space, simpler hypothesis space, so that smaller VC dimension can give us a smaller, this term gives us a tighter generalization error bound. And of course, if you want a larger delta, if you want a smaller delta, right? If you want a smaller delta, means with a higher chance, then this term will be larger as well. Right? So any question regarding understanding of this result? Hopefully, connecting our previous analysis and also the definition of this dimension can give us a good understanding about those classical results. This is really most insightful research result of the PAC learning in the past 2 decades. Right? And we'll actually use that to derive the support vector machines. Right? So now I want to make connection between the computational learning theory and also the practical machine learning algorithm, right? So we know that many computational learning theory, they just wants to address some interesting theoretical questions, like for example, if a target function is weakly learnable, right? And then an interesting question that can we use or based upon those weak learnable classifiers or concepts to derive like stronger learning algorithm, right? This actually motivates the invention of the boosting and ADA boost. Right? So now from the another line of analysis using probability bound, VC dimension, all kind of stuff, we can derive that with high probability, your generalization error is upper bounded by your training error plus a term with delta. Delta is the confidence level, and also your visit dimension, which indicates the expressivity of your hypothesis space. Then the question is that, can we develop a practically useful algorithm based upon that? This algorithm tries to minimize this generalization error bound. And that is the support vector machine we're going to discuss in the next step. And this learning principle, namely, we want to minimize the generalization error bound. This is called a structure risk minimization principle. Right? So they call this risk, right? They call this guy as a risk. And this have structure, right? We have training error plus some bounding term, right? We want to minimize this risk so that we can get a good estimate of the generalization error. So this principle is called structure risk minimization principle, and the most prominent example is support vector machine. Okay, so now we're gonna look at support vector machine. Support vector machine is a classical, yet very popular, very widely used machine learning algorithm. So I want to share a bit history about support vector machine, right? So in 1980s, the whole time of 1980s is about like resurgence of neural networks, like because people find that if you're doing some nonlinear transformation, like that is neural networks, they can overcome the limitation of perception. Right? Remember, perception cannot classify like XOR examples, right? The parity examples, but neural network can handle that. Right? And the backpropagation was invented during that time. Right? But then in the early 90s, oops, what happens? That's weird. Okay, that's weird. Let me sorry, what, I don't know what happened to this projector. Yeah, let me plug in again. Okay. 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 Okay, looks good. So in early 90s, SVM pops up, and then immediately attracts like huge number of huge amount of attentions, and then people quickly give up neural networks, and people are like surprised by this elegance. It's not only like, okay, they're practically useful. At that time, actually, SVM can outperform or be comparable to neural networks. However, SVM is based upon computational learning theory. It's much more rigorous. So this topic is hot for like about 20 years. Right? And then in I think it's 2006 or 2012, the group of Jeffrey Hinton, they make the neural network popular again. Why? Because they show that the neural network can give like dramatic improvement on some image classification task, and then they call it AlexNet, right? So, and then like all the industry and the research community started to switch to neural network again, right? But here I just want to emphasize that support vector machines, you can feel like they're quite mature, and they're kind of like standard tool in almost all kinds of like machine learning libraries, right? In many cases, like if your data set is not large, right? It's quite sparse, and you don't want like running GPU or clusters to train a large big model. You want to have quick development of those models. So the first choice will be support vector machines, and it works pretty well and quite robust. So here, just a set of successful applications of support vector machines, which are I'm not gonna I'm gonna explain in detail, right? So before we talk about support vector machines, right? Let us first step back and look at the big picture. Right? We haven't discussed many learning algorithms and methodologies so far, right? We don't want to confuse ourselves. Right? We want to organize them. So far we're talking about linear model, right? And based upon how good is a linear model, right? We define different evaluation strategy on the goodness of linear classifiers, which motivates us to develop different learning algorithms. Like the first one is perceptron. Perceptron essentially is mystic-driven learning algorithm. Right? We only care about whether it can correctly predict the training examples or not. Right? If it's not, then we're going to update our model. Otherwise, we just stay. It is a lazy training. So it gives us the perceptron. Right? If we want to evaluate the goodness of our linear classifiers in terms of the PAC learning framework, in agnostic learning framework, that means we cannot just look at the training error, right? Zero training error does not necessarily give you a good generalization error, right? We need to look at the generalization error, and the generalization error can be estimated by some bound, right? Generalization error bound. So then the idea will be naturally to, okay, how can we, minimize the generalization error bound that gives the risk minimization principle, and the prominent example will be support vector machines. And of course, there can be other choices, right? You can invent some new evaluation strategy on your linear models, with which you can develop your own learning algorithms. So for support vector machines, here are the topics we want to discuss. First, we're going to explain why the support vector machine use the training strategy of maximizing the margin. Right? So actually briefly discussed before, right? Intuitively, we're going to prefer your linear classifier to have a large margin, right? But why should we do that? Right? We're going to connect it to the generalization error bound we have just discussed. Right? Then based on this maximizing margin principle, we'll propose the so-called SVM objective function. You see that the naive or straightforward formulation will be very hard to optimize. Right? We're going to use some like insights of linear classifiers to simplify. Right? Then, given the SVM objective function, we'll talk about how to solve SVM optimization problem. And finally, we'll talk about how to extend support vector machines to nonlinear classifiers. Right? Remember, support vector machines, originally, they're just linear classifiers. Right? Of course, we want our linear classifiers to handle nonlinear classification problems. How can we do that? Right? We're going to introduce the so-called kernel tricks, and also you will know the dual space and primal space, and also you know why they are called support vectors. Questions? Yeah. No, we're not gonna generalize that. We can discuss about later, because there are like two simple strategies to generalize them. But for simplicity, And for convenience, we're going to focus on binary classification problem. What? SVM regression? No, we're not going to talk about SVM regression. But usually SVM, people won't use SVM to do regression. SVM is mostly used for classification. For regression, you have a lot of other choices. No, we're not going to talk about that. But if you want to talk about it, we can discuss about it more like in office hour offline. So you see that actually the extension or generalization of SVM to nonlinear classifiers is a very elegant approach. Okay? And we leverage some concept in the optimization, but don't worry, we will not go to the deep details about optimization. We're gonna just introduce some like the basic concepts like KKT conditions. You're not required to memorize them, but you do need to understand the logic chain to derive the SVM dual. And in the dual space, you will see why they are called support vectors and how the kernel trick is smartly embedded into this procedure. Okay. So overall, this piece of topic, support vector machines, they won't give you a heavy load of programming. So you see that in your homework, or your implementation of support vector machines may be less than 10 lines. Right? But we do need to spend some time understanding the idea, the underlying idea, because they will involve a bunch of like logic chains based on different mathematical details. So it's not hard, but it's a little bit long. Okay. Okay. So first, let us talk about the training principle of support vector machines. That is, we want to maximize margin. Right? So from the generalization error bound we have derived so far, right? This is the generalization error bound. We do not require our hypothesis space to be finite. Right? It can be infinite, right? Because we have VC dimension. Right? The classical theory tells us, right? Suppose we have M training examples, then with high probability, right? 1 minus delta, right? The true error of your learned hypothesis, whose training error is here, right? The true error can be bounded by the training error plus a term determined by your VC dimension, right? So from this generalization error bound, we can immediately see that if you have a choice to select the hypothesis space for the same level of the training error, I want to pick up the one who has the smallest VC dimension, right? Because it will make the bound tighter. It will make your estimate of generalization error smaller, right? Now, can we apply this theory to linear classifiers? We have already listed the VC dimension of linear classifiers. Unfortunately, the VC dimension of the whole linear classifier space in D-dimensional space, I mean that you have D input features, is fixed. It's D plus 1. So it seems that okay, if you just run linear classifier, right? Here's your estimate of generalization error. The VC dimension is fixed, right? And how do you pick up? How do you minimize the VC dimension? It looks like it's infeasible, right? So here's the how can we smartly get rid of this problem? Right? So when we search our linear classifier in the whole possible family of whole possible linear classifier candidates, of course, the VC dimension is D plus 1, is fixed, right? But what if we restrict our search space into a small subsets of linear classifiers, right? So you can imagine you have a big family of linear classifiers, right? Their VC dimension is simply fixed, is D plus 1. If you search over the whole space, well, you don't have any improvement over the generalization error bound, right? However, if you can smartly pick up a subset of linear classifiers, you just search over this small subset of linear classifiers, then we can imagine the VC dimension will be reduced, right? So you can tighten your bound. So that's the key idea, right? We want to consider different subsets of linear classifiers. We want to pick up the one who has this dimension to be as small as possible. Then the problem is that how do we define or pick up the subsets of linear classifier, right? According to which metric? That relates to the concept margin we previously discussed. Right? So let us review the definition of margin, right? We say a hyperplane has a margin for a particular data set. That means first, this data set is linearly separable, right? And secondly, this hyperplane can separate positive examples from negative example, gives 0 prediction error. Then the margin of this hyperplane for this data set will be the minimum distance between the points in the data set and this hyperplane. Right? This is the definition of margin. Right? And also we discussed for a linearly separable data set, right? Suppose you have many separating hyperplanes. Right? Different hyperplanes will have different margins. Which type of hyperplane would you like to choose? Right? The one gives larger margins, right? We discussed this, right? Suppose you got H1, H2, and both are like perfectly can perfectly separate the positive and negative examples, right? But the margin of H1 is larger than the margin of H2. Right? We're going to choose H1, and we'll give you some like intuitive explanation in terms of probability distribution, right? So the rationale is as follows, right? So if you have a smaller margin, right, that means you get closer to the training points, right? Like H2, right? That means you're more likely to pass through the high density regions of those positive labels, negative labels, right? So if you look at H2, right? So it is much closer to the positive and negative examples than H1. That means it takes much more risk to pass through the high density regions. Then that means surrounding the classification boundary, it could appear both positive examples, right? So if it is in this side, okay, you make correct prediction. But the positive examples can also have a high chance to appear on the other side of H2. That means you're likely to make mistakes, right? Right? We haven't done this analysis before, right? And similar observation can be applied here, right? So H2 also pass through the high density region for negative examples. That means it's very likely that some negative examples in the opposite side of the hyperplane, so it gives wrong prediction, right? So it takes much more risk to give wrong prediction because you pass through the high density regions, right? On the contrary, if your hyperplane has large margin, that means it gets farther away from both positive and negative examples. So that means it is less likely, much less likely to pass through the high density regions. So that means on the other side, it will be very unlikely that some positive examples appear here or some negative examples appear on here, right? Why? Because they're low density regions, right? So that means H1 is much less risky to misclassify examples. So that's the intuition we have, right? When we talk about, okay, how do we select hypotheses or linear classifiers according to their margin. And then how do we give a rigorous justification, right? Not just from some intuitive analysis, right? So here, we introduce the so-called data-dependent least dimension. Right? Remember, we just talk about how do we reduce the generalization error bound. Right? So we talk about, okay, if you search over the entire space of linear classifiers, there's no hope because the least dimension is fixed. Right? Now our strategy is that I want to pick up subsets of linear classifiers inside that, right? Because you reduce the space, your Viss dimension can be smaller. So your generation error bound could be tighter. Right? So how do we define those subsets of linear classifiers? Right? We can use margin. Yeah. Yeah. Yeah, that's something we're going to discuss right now. Yeah. Right. We just talk about the strategy, right? We want to find the subsets. So we can, like, intuitively, we can imagine, okay, for this big fixed space, the Viss dimension is there, right? But if we just pick up a small subset, your Viss dimension can be smaller, right? Although both spaces can be infinite, it's possible, right? But as we discussed, right, Viss dimension can compare the expressivity for infinite hypothesis spaces. Does it make sense? Right. So then the question is that how do we define different subsets of linear classifiers? Right? So here we're gonna leverage the concept called margin. Right? How do we define that? Right. So we consider linear classifiers with margins gamma 1 and gamma 2. Right? So actually you can look at all the separable linear classifiers, right, with different choice of margins. Right? If we define H1 as linear classifiers that have margin at least gamma 1, and H2 as another subset of linear classifiers that have a margin at least gamma 2. And suppose gamma 1 is bigger than gamma 2. Right? Intuitively, we believe that the set of functions H1 is better. Right? Why? Because overall, the linear classifiers H1 has larger margin than H2. Right? So you can see that if you use margin to index different subsets of linear classifiers, seems that it can guide us to find out a good subset of linear classifiers. Right? So now we reach to the K theorem. Right? If we define H to be the set of linear classifiers that separate the training set by our margin at least gamma, right? Then what's the Viss dimension? Right? It's hard to compute the Viss dimension, but Vapnik gives the theory that we can bound Viss dimension. Right? The Viss dimension is no bigger than the minimum of R squared over gamma squared, the input dimension D plus 1. Right? So what is R? R actually is the maximum length of your input vectors. It's the same as the Misty bound theorem we discussed for perception. Right? R is the maximum norm of the training input vectors. Right? And gamma is actually the margin we select. Right? And D is the input feature plus 1. Right? And R, you can also view as the radius of the smallest sphere containing the training data. Right? So what does this theorem tell us? Right? Actually, it gives us a quantify how expressive of a different subsets of linear classifiers indexed by the margin gamma. Right? So from the theorem, it immediately tells us, okay, the larger the margin you choose, the lower the Viss dimension of the subset of linear classifier indexed by gamma. Right? And from the computational learning theory, we know that the lower the Viss dimension you have, the better the generalization error bound you have. Right? So now, naturally, we'll have a learning principle. Right? If we want to maximize the margin, that means you're trying to search over a subset of linear classifiers who has the largest margin. Then you kind of maximize or minimize the Viss dimension, and then you want to obtain the tightest generation error bound. That's the whole reasoning of maximizing margin principle. Okay. So the computational learning theory actually makes the connection between the margin and the generation error bound. If we want to find a linear classifier that maximizes margin, it is equivalent to tighten the generation error bound. Okay. That's how we derive the training principles for back machines. We want to maximize margin so as to find a smallest generation error bound. Yeah. Oh, it's nothing to do with the input dimension. You can just feel like, okay, this is a whole set of linear classifiers, right? Each linear classifier can give a prediction over d-dimensional training input, right? Or any test input, whatever, right? If you just search over the entire space, well, your visit dimension is there, is d+1 is fixed, right? Then the strategy is, okay, why not just pick up a small subset, right? Remember, this small subset, each classifier in this small subset still predict or labels d-dimensional inputs, right? But because it's a small subset, the visit dimension can be decreased. Right? And maximize the margin is equivalent to like finding out a searching over a small subset who has the smallest margin. Who is the smallest visit dimension? Sorry. There's nothing to do with that. Yeah, you can pick up any. It depends on your application, right? In this case, I'm 10 features. Okay, it's just a 10-dimensional classifier, right? Another 100 features and 100 dimension, right? All those reasoning still applies. Right? Any other question? This is very, very important for us to. Yeah. But here we assume that, okay, once you choose a particular problem, particular classification problem, your D is fixed, right? And your training set is there. That means your R is fixed, right? And then the problem is that, okay, how do we restrict our search over a subset of linear classifiers, right? And then we pick up the one indexed by the largest margin. Yeah. So don't get confused about D and R here. D and R are fixed as long as you pick up a particular problem, a particular task, and given the particular training set, they are fixed. Then the remaining question is how do we optimize our learning procedure? Yeah. Yes, exactly. This one?
Yeah.
Yeah, that's a very good question. So here, let us assume the training error is the same. Yeah, that's a very good question. When we talk about soft SVM, you see the trade-off. But here, our pre-assumption is that, okay, we can maintain the same training error. However, if at the same time, you can reduce the visit dimension, of course, you can make your bound tighter and tighter. That means you can get smaller and smaller estimate of the generation error. Another question regarding the learning principle of SVM. Yeah. The margin is for the whole data set, right? So that's that's a good question. So that leads to how do we formulate the objective function? Yeah, I think that's 3 minutes to. So let's stop here today, a little bit early, because you see that if you want to max margin, right? And essentially do bi-level optimization. Why? Because in outer level, you're gonna optimize your parameters like W and B, right? But in the inner level, you need to compute the margin. Compute margin that you have to go over the entire training data. So that will be very, very costly. So on Thursday, we'll talk about how do we make this objective a lot simpler to optimize. Okay, see you on Thursday.